Hi everyone. I want to talk to you a little bit about conditional probability and a few other probability topics that weren't covered in the last video. So let me pop over to the notes and start doing that. So the first thing I want to talk about is conditional probability, which is really important. Like it's a very important idea in probability because sometimes you want to figure out what's the probability of something happening if you already know some other information. So usually we think of that is what's the probability, or the way we think of that is we ask about the probability of some event occurring if we know that some other event has already occurred, right? That's the way we do that, and it's written like this. Right, so this says probability of A given D. So I'm going to be referencing the same chart that I was using in the last video, this guy right here. The events A, B, and C, and D talked about this. So event D that I was just mentioning. So D is going to be the event. The first roll is a 5, right? So we know that roll 1 is a 5, and then we want to know what's the probability that we get that the total of the dice is at least 10. Oh, I'm sorry, there appears to be a typo in the notes. That should be probability of C given D. I apologize. Because event C was probability is at least 10, or the total is at least 10. So this is really what I meant, probability of C given D. Sorry about that. Let's just go ahead and fix that. Go ahead and save that guy. And so the probability of C given D, if D is the first roll is a 5, well, let's go look at them. Here's how we can use that. So we know that the first roll is a 5. We already know that this is true. Therefore, we don't have to consider all the other cases for the first roll. I can ignore the cases for the first roll being 1, 2, 3, 4, or 6, right? Because I know it was a 5. We're just looking for the probability of C given that the first roll was a 5. And let me just remind you, I'll go ahead and annotate this, even though it's just going to get deleted as soon as I leave the screen, that event C was these 6 outcomes right here where the total was 10, or total is at least 10, right? So two of those are also in this new event D, which is that the first roll is a 5. So that means that of the 6 events in event D, 2 of them fall into the category that I'm looking for. So the probability that the total is at least 10, given that the first roll was a 5, is 2 out of 6. So let's go back to here, and we'll see a little bit more of that. A good intuition for the way the way to think of this is that the probability of X given Y is the probability of X happening if Y has already happened, or if we know that Y is going to happen or is true for sure. So one thing to note in this notation, it kind of looks like the X and the Y have sort of parallel importance in the notation, and they don't. They're totally different. So probability of X given Y is really the probability of X. The given Y part is just a restriction on the sample space. This right here is the probability of X within Y, or within event Y, right? So the denominator of your fraction isn't 36, or isn't the whole sample space. It's just how many things are in Y rather than how many things are in all the possible outcomes. We're only concerned with the outcomes that are within Y. So this really says the probability of X within with our sample space restricted to just event Y. That's what that means. So I'm going to go ahead and find these things. I don't know if I'm going to necessarily find all 6 of these. Maybe we will. It's not that bad. So I'm going to go ahead and go back to my other screen, put A, B, and C up there, and find a bunch of probabilities. So let's go ahead and do that. I'm going to switch back here. And so if you remember, A was the first roll is 2 or less. I guess I'll just re-annotate all this. A is the first roll is 2 or less. Hello? Are we not annotating? Sorry. I don't know why it's doing this. What the heck? Okay, great. Seems to be working now. A was first roll is 2 or less. All right, that's A. The second event B was that the first roll, or excuse me, the second roll was even, so it was these guys, right? Ones with in the columns 2, 4, and 6 here. All right, so it's B. And then C was that the total was at least 10. So that was these guys over here. Okay, so what I want to do is I want to find probability of A given B, B given A given C given A, B given C, and C given B. And see what things we can figure out about that. All right, so we've got probability. I'll leave myself a little more room here. Probability of A given B. So remember, this really means the probability of A if we're only looking at the B, or if we're only looking at event B. So if I'm only looking at event B, that's just the green outlined ones. I'm ignoring all of the things with an odd second roll. Within B, and remember there's 18 outcomes in B, how many of those things are in A? The answer is 6, right? These 6 right here that are in both. So this is the 6 events that are in A within B. So it's going to be, this is 6 out of 18. The probability of B given A, even though the notation makes it look like, oh, those are probably the same because it's the same letters in there, it's not. So remember that A and B here don't play the same role in this probability statement. This is the probability of B given that we are looking only in event A. So within the 12 outcomes in A, how many of them are in B? The answer is 6. It's the same 6, right? It's the same ones that are in both that are in the numerator here. So 1, 2, 2, 2, 1, 4, 2, 4, 1, 6, and 2, 6. Right, so those guys are the numerator. So there's 6 events, but now I'm looking, or excuse me, 6 outcomes, but I'm looking within only event A, which means there's 12 outcomes total. So this would be 6 out of 12. And notice that those are not the same, right? This is a third and this is a half, right? Same probabilities are not the same. It depends on what order you are going in here. So we'll do A given C and C given A, and those will be quick. Probability of A given C means that we are going to look within event C and ask ourselves, there's C there, and ask ourselves how many outcomes are in A. The answer is none of them, right? There's nothing that's in both A and C. So there's 0 outcomes out of the 6 here. So probability of A given C is 0, and the probability of C given A also 0. That, by the way, will always be true. If the probability of A given C is 0, the probability of C given A will also be 0 every single time. You'll see why when we get to the formula in just a second. So the probability of C given A is 0. And then we'll do the last two, probability of B given C and C given B. Probability of B given C means, again, we're going to start with the given part, which is to say we are looking in C, and then within that, what's the probability of getting B? Well, there's 6 events in C. 4 of those events are also in B. So that means that the probability of, if we know we are in C, we know that the total is at least 10, what's the probability that we had an even second roll? And the answer is 4 out of 6. Right? These 4 events out of the 6 in C. So this guy's 4 out of 6. And then I ran out of room a little bit here, so I'm just going to go over here. Probability of C given B. So now it is, given that we know that we have got an even second roll, what's the probability that we get a total of at least 10? Well, if we know we have an even second roll, then I'm looking in event B here, right? So that's the green stuff. What's the probability that we get a total of at least 10? Well, there's 4 events within B that have a total of at least 10. So 4 out of the 18 events, or 4 out of the 18 outcomes. So this guy is 4 out of 18. Okay, keep those things in mind. Let's see if I can remember what those are. So we got 6 out of 18, 6 out of 12, 0, and then 4 out of 6 and 4 out of 18. So you might want to write those down. I'm going to go ahead and just remember them, and because we're going to use those in just a second. But that's conditional probability. The way you want to think of conditional probability is it's a restriction on your sample space. If I restrict my sample space to just this second thing, right, just the outcomes in this the second event, the event after the given bar, then what's the probability of this first event, right? So the conditional probability is a restriction on your sample space to the second thing, to the thing after the given bar, and then you find the probability of the thing before the given bar. All right, so with those things in mind, let's go back and look at what questions we asked here. So delete everything, of course. The AND rule, and then I want to talk about independence. This turns out to be super important in probability, as does this. To be honest, I'm really only giving you the big highlights here. So we found all these things, found all those a probability of A given B given A given C, etc. And then I wanted to point something out, that the probability of X given Y is the probability of X and Y over the probability of Y. We actually saw that when we were doing this. I'm going to go ahead and go back to my other sheet and do that with A and B. So we had A was this. It's doing it again. Why is it not annotating correctly? We got this one. All right, there's A. And then B was these guys. Let's think of B. So when we found the probability of A given B, we restricted ourselves to just look at the outcomes in B, right? So that was our new denominator, was how many outcomes are in event B. And then the numerator was, well, okay, how many of the ones in B are also in A, which is to say, how many outcomes are in A and B divided by how many are in B, right? Because our new sample space is B. And that's all the formula is. The formula says that the formula says that the way you calculate probability of A given B is you take the probability of A and B, so how many events are in A and B, and divide it by the probability of just B. So in other words, just the things in B that you're looking at. And that's exactly what we did here, right? We just looked at, well, there's 6 events in both out of the 18 in B, which is our given. So it's 6 out of 18, and that's it. And that is what the formula says. Probability of X given Y is probability of X and Y divided by the probability of Y. Now, one nice thing about this is if you look at this, you can see that the Y, that's the thing in the denominator here. And this sort of looks like a fraction bar. Don't write it as a fraction bar. It's a vertical line. Don't like make it diagonal or anything. That'll just be confusing. But the given bar, if you sort of think of it as a fraction bar with this thing on the bottom, that actually works out pretty well, right? Because it can often be hard to remember which thing you are, or which, what the formula is, given that we just have a bunch of letters here. But it is the probability of both of them divided by the probability of the one that you are restricted to. That's how you calculate conditional probability. Your book calls this the multiplication rule. I called it the AND rule here, but that's probably a bad name too. Conditional probability formula is the thing that is the thing that I'll call it in the future, and I think I'll probably change my notes probably for next semester, so you don't have to go relook at them again. So you don't have to go edit yours. But there you go. Conditional probability formula is this. This can also be rearranged, by the way. So so these are all numbers, right? So probability of X given Y, that is a number. This is a number. This is a number. So if I multiply both sides by probability of Y, the thing that I get is this, which is an alternative form of the same thing. The probability of X and Y is the probability of X given Y times probability of Y. Yeah, there you go. You may have seen something like this in the past. like this, probability of x and y equals probability of x times probability of y. Be really careful with this because that's not usually true. That's true some of the time. It's true if x and y are what are called independent events, which is not generally the case. Generally speaking, most things that you're calculating the probability of are not independent. Things that are independent are like dice rolls, right? The first roll doesn't affect the second one. Or if I flip 2 coins, the outcome of the first flip doesn't affect the outcome of the second flip. Those things are independent, which we're going to talk about next. But in general, don't use this formula. I have people do this all the time, but don't use that most of the time. If you know the events are independent, you can go ahead and use it, but most of the time they're not, and so most of the time you'll end up being wrong if you try it. So the one you want to use is this one right here. Well, one of these, right? Like that's the right formula. This formula works all the time, regardless of what type of events you have. This is always true. Okay. So I know I've been kind of throwing a lot of formulas at you. We had the OR rule in the last video. We've got the multiplication rule here, or the conditional probability formula here. And luckily, that's basically all of them. Like, we're not really going to use any more formulas besides those. So when you're trying to figure out a probability that involves some calculations, just ask yourself, well, which ones of these could I use? Okay. And a really, really important definition in probability is independence. 2 events are independent if one of them happening does not affect whether the other one happens. So in other words, x and y are independent if the probability of x given y is the probability of x. So that's just our mathematical formulation of the thing that I just said. Notice that the probability of x given y means the probability of x happening if y has happened. And the probability of x is just the probability of x happening regardless of y. So what this says is, if these 2 things are the same, so in other words, the probability of x, if y has happened, is exactly the same as the probability of x in general, then y happening did not affect the probability of x. Therefore, x and y are independent. You can also write that the other way, by the way, probability of y given x equals probability of y. If one's true, the other one will always be true, so you don't actually have to check both. So I'll just quote this one. But really think about what this means. And this is where statistics starts getting kind of hard. Well, not like this point in time, but this is the sort of thing that makes statistics hard, where this is a really complex idea, like what it means to be independent. Why does this formula tell me what it means to tell me that those 2 things are independent? You have to really think about what these 2 things mean, translate them into some sort of meaning in your mind, and realize that when those 2 things are equal, that means that one did not affect the other. So this is really tricky. Take some time to absorb this. Feel free to pause the video here and just think about that. Certainly not a bad idea. It's very hard for you to listen to me and also think deeply about what I'm saying. So feel free to pause, of course. You won't hurt my feelings if you pause. Yeah. In events where this is not true, where probability of x given y is not the same as the probability of x, those are called dependent, obviously. So I want to talk about the events that we saw before that were independent or dependent. The events of the dice roll, the roll 2 dice experiment. Yeah, and then I'll come back to number 7 in just a second, because that often confuses people. So let's go back to this same sheet that where all the notations keep getting deleted. And I'll let you look up the various probabilities, but go back to the things that you've written down and look up the probability of A and the probability of A given B. Right? So probability of A, I want to annotate this. The probability of A was 12 out of 36. All right, here's A. So the probability of A was 12 out of 36. And the probability of A given B, so let's put B on here, was 6 out of 18. All right, so we had probability of A was 12 out of 36. The probability of B, nope, that's not what I meant. I meant the probability of A given B. That's what I meant. Was 6 out of 18. And those are the same number, right? Those are both a third. This is where it helps to reduce your fractions, by the way. This is 1/3 and this is also 1/3, and those numbers are the same. So the probability of A equals the probability of A given B. In other words, the probability of A happening is a third, and the probability of A happening if B has already happened is also a third. So B happening didn't change whether A can happen, or didn't change the probability of A happening. So these guys are independent. On the other hand, if I look at the probability of A and the probability, or let's do B and C. Yeah, so the probability, so here's C right here, right? There's C. So the probability of B was 18 out of 36. And the probability of B given C was 4 out of 6, right? So if I restrict myself to just looking at C, there's only 6 outcomes. 4 of them are in B. So this is 4 out of 6. Those are not the same. Probability of B is a half, and probability of B given C is 2/3, right? So not the same number. So these are dependent. All right, I've explained this in terms of just the formulas, the formula that you use, like check to see if two things are equal or not. But it maybe makes more intuitive sense if I explain it a little bit differently. Probability of A, so A is a statement about the first roll, and B is a statement about the second roll. I would not expect one roll of the dice to affect the other one, and it doesn't, right? So if the first roll is, whether the first roll is a 1 or 2 is not affected by the second roll being even or odd. And so you would expect that A and B, a statement about the first roll, and B, a statement about the second roll, would be independent of each other, and they are. On the other hand, event C talks about the total of both rolls, right? So one roll affecting the total, one roll is going to affect the total, right? So the whether you're in event C is going to depend on what your rolls were, or what each of the rolls were, and that's true here, right? If we know we are in event C, then it is more likely that we had an even second roll. And similarly, if I did A or A given C, by the way, the probability would be 0, right? We already know that the probability of A given C is 0. And so what that is saying is, if I know that my second, or that the total of the rolls was at least 10, what's the probability that my first roll was 2 or less? 0, can't be, right? If I know that the total is 10 or more, then the first roll can't be 2, because that prevents the total from being 10 or more. And so whether we are in whether we're in A or B is affected by whether we know we're in C, and vice versa. The probability of C given B would also not be equal to the probability of C, right? I'll let you calculate all those things, but, well, I'm not going to stop you. I will encourage you to calculate all those things and make sure you know how that calculation is done. But whether we are in A or B is affected by C, but the probability of being in A is not affected by B, because those are about two totally unrelated things, the first roll and the second roll, whereas the C is related to both of them. And you can see that in the probabilities. So that's what independent versus dependent means, is does one of them happening affect the probability of the other one happening? And if it does, they're dependent, and if it doesn't, they're independent. You can see why I didn't necessarily want you to use the formula for x and y being probability of x times probability of y. That works if the events are independent or if the events are independent and not if they're dependent. But as you can imagine, we deal with dependent events a lot, and there's no need to remember two formulas. You can just use the probability of x and y is probability of x given y times probability of y. And that just works all the time. You don't need a second formula. Okay. Let me go back to the notes for a second here. I think we are nearly done. I guess we're going to do Venn diagrams and then the OR rule, which I already explained, but I'll explain in terms of Venn diagrams again. Okay, so here's what a Venn diagram is. You've probably seen them before. It's two overlapping circles, essentially. And each of the circles represents an event. Event A, event B, and the bit in the middle is event A, or is where both of them are true. That's A and B is the bit in the middle here, the purple bit in this picture. Should also be a box around this. I'll do an example here in just a second. And Venn diagrams are great visualization tools. I really like them as visualization tools. In fact, I used one just the other day to help me calculate a relatively complex probability. But they're a little bit hard to fill out until you see them. There should be, I'll show you this in just a second. There should be another box out here. So the place I want to go for this is down to the bottom here. My last example are some events. I'm gonna do the first one, or just this first one right here, A, B, and B given A. And I'll show you what we can do with this. And again, A and B don't refer to the same thing that they did before. So let me go ahead and make a whiteboard so that we can look at these. I'm going to write all this down. Probability of A is 0.5, B is 0.4, and B given A is 0.3. All right, so let's clear all this off. So we've got probability of A is 0.5. Probability of B is 0.4. It can be easier to think about these in percentage terms, by the way, if you would like. Did I give B given A? Yeah, B given A is 0.3. Okay. So from here, the first question, and I'm not going to, I guess I can actually flip back here because this is a whiteboard rather than annotation. So the first question here is find the probability of A and B. You might ask yourself, well, how the heck can I do that? Right? Like this doesn't look like a thing we know how to do. It actually is. This is actually very simple. We only know two formulas, right? They are this formula right here, which is equivalent to that one, and this formula. That's all we got. So the one I'm going to use, because I have conditional probability, right? I have B given A, that makes me want to use the conditional probability formula. So that's obviously what I'm going to do. So I can say that probability of B given A is 0.3, and that's equal to the probability of A and B over the probability of A. B and A over A, I suppose. Let's go see that on the whiteboard. So I can say that the probability of B given A is the probability of B and A over probability of A. Now, let me point something out. B and A and B are the same exact thing. There's no difference between the two. It does not matter what order you write and or in, but it does matter what order you write the conditional stuff in. So you can think of this as probability of A and B if you would like, or probability of B and A. It is exactly the same thing. So this says probability of B and A, or B given A, we know is 0.3. Probability of A and B, or B and A, I guess I'll be consistent here, is the thing we're looking for, and then the probability of A was 0.5. So all I have to do to find the probability of B and A is multiply both sides by 0.5, and then I'm done. Right? Just do a little algebra here. This is an actual equation. And so when I do that on the right, cancels out. On the left, I get 0.15, 0.15 equals probability of B and A. I don't know why I didn't write parentheses. There we go. And that's it. That's all I got to do to find those. So I know the probability of A and B, or B and A, is 15%. I'm going to go ahead and write that down. Probability of A and B. That will be relevant for us in just a second. And now what I want to do is I want to make a Venn diagram of these two things. I'm going to go ahead and clear all this stuff off. Yeah, that stuff right there. I want to make a Venn diagram of this. And so my Venn diagram looks like this. That it is selecting rather than writing. Gosh darn it. I wish it would not default to making me reopen it every time. All right. I know the Venn diagram picture I had in the notes didn't look exactly like this because it didn't have a box, but it should have had a box. Now I'll show you why. This is going to be A, and this is going to be B. So what I want to do is I want to fill out a Venn diagram for this information, for these events, because it'll help us visualize, well, a bunch of stuff, but I'll show you in just a second. So the way you want to fill out your Venn diagram, all right, so here's the idea. Everything in the A circle has to total up to 0.5, but don't just put 0.5 in here. That's wrong, because everything in A includes this crescent bit and also this bit in the middle. The same thing for B. 0.4 does not go in here. The total of these two things is 0.4, right? And so we have to start from the middle, where we know which things they share. So the probability, that's this middle bit are the things that are in both A and B. So this bit is 0.15 or 15% if you like. Now, some people really don't like the decimals. I'm fine either way, whichever one you want to do. All right, so there's 0.15 is the bit in the middle, and now all the stuff in A has to total up to 0.5. But we've already got up to 50%, and there's already 15% of it right there, leaving me only 35%, right? So 0.35 goes here. And similarly, 0.25 goes over here. Now, the reason I wanted this box is that this box is supposed to contain all of the possible outcomes, right? A and B are not necessarily the only events in our sample space. It's entirely possible that there's others, and in fact, in this case, there are. Right, so this total right here, if I add it all up, is only 0.75, which leaves me 0.25 outside. So there's 0.25 or 25% that's not in either one. Right, so just because all I've given you is A and B doesn't mean that's all that could possibly be. That's all the possible outcomes. Right, there's in this case 25% of the outcomes are not in A or B. Okay, let's go back and look at another question. So question B was make a Venn diagram, right? So there we go. I want to find the probability of A or B and the probability of A given B. Now, we have probability of B given A, but not A given B, which we'll get back to in a second. So A or B and A given B. So the way I'm going to do A or B, you can actually use this Venn diagram to help you, or you can use the formula. So I'll do both, right? A or B means in A or B or both. So that means we just add up these three numbers, which is 0.75. So for my Venn diagram, I can just see that it's 0.75 with just a little bit of addition. We can also do the formula, right? And remember that our formula for OR was probability of A or B is probability of A plus the probability of B minus the probability of A and B. And again, what we're doing here is we're counting up all of A, so we're doing all of this, and then we're adding on all of B, so we're doing all of this, and then we realize, oh, I've counted this bit twice. I've sort of got two layers of this middle bit. Let me take one of them away so that now I'm only counting it once. And so when we do that, I would get 0.5 plus 0.4 minus 0.15 equals 0.75. right? So we can see it from the formula, and we can also see it by just thinking about what OR means. OR means all the stuff in either circle added up. 0.35 plus 0.115 plus 0.25 is 0.75. Same deal either way. So you can use the formula, and I'll go ahead and write that up here. Probability of A or B equals 0.75. And of course, I'm going to erase this calculation down here for room. Nope, I didn't quite get all of it. Where's my eraser? Okay. Okay, so what else were we finding? I don't remember. A given B, and then we're going to ask about independent or mutually exclusive. So I want to find the probability of A given B. I personally think that's easiest to do from the formula. That's the probability of A and B over the probability of B. You can totally just plug in, which is why it's easy. And I'll explain how you can see it on the Venn diagram as well. This was 0.15 over 0.4, which is 3 out of 8, so 0.375. There you go. Right, so that's probability of A given B. The way you can see this on the diagram is you can just look. So we know we're restricted to B, so I am looking only at B here. There's a 40% chance that I'm in there, and then within that, there's a 15% chance that I'm within A. So it's this 15% out of the 40% that I'm considering here, which is exactly what the formula is, right? The formula just tells you to do that. So you can look at it either way. I like both, to be honest. I like thinking about it both ways because one cements the other one in your brain, or at least it does in mine. I hope it does for you as well. So 0.15 out of 0.4 is 0.375, and then I'm done. So that's how you calculate the other given probability. All right, and then the next two questions were, are A and B independent, and are A and B mutually exclusive? So let's do independent first. So probability of A and the probability of A given B. So that's what I'm going to look at. So probability of A equals 0.5. Probability of A given B equals 0.375. Dependent, right? Those are not equal. Right, those are not equal, so it's dependent. You actually could have told that just from the given information, right? Probability of B and probability of B given A were not the same. One's 0.4, the other one's 0.3. The events are dependent. You don't have to check both. You can just check either B and B given A or A and A given B. That works. Either one works. Because if it's not independent one direction, if it's dependent one direction, it's dependent both directions. The same for independent. And the other question was, are they mutually exclusive? And the answer is no. Mutually exclusive events have no overlap. And this overlaps by 15% here. So there are outcomes in event A and also in event B. In fact, 15% of the total outcomes are in there. Similarly, you can also tell that they're not exclusive or not mutually exclusive by the fact that B given A here was not 0, right? If they were mutually exclusive and we knew that A happened, that would mean that B would then be precluded. It would be prevented from happening, right? That's what mutually exclusive is. One prevents the other one. And this says, what's the probability of B if we know that A has already happened? Well, it's not 0, so they're not mutually exclusive. All right, and so I've got 2 more of these for you to do as well, right? If we were doing this in a regular class, I would just have the whole class work on all 3 of these. In fact, the way I do this in class is we do these together, kind of talk through it as a class, and then the students do these guys. Let me point out a couple of things about these. When you try these yourself, I would highly recommend that you try them yourself. Probability of F given E here is the same as the probability of F. That should tell you something, What should that tell you? Similarly, the probability of D given C here is 0. That means if we know C has happened, then the probability of D becomes 0. What does that tell you? Let's tell you interesting things. Okay. Yeah, we'll do a little bit of this stuff. Okay. So we talked about the OR rule, right? We talked about it in the last video, and also just on the previous screen, on the whiteboard there. And yeah, it's just this picture will help you visualize that, I hope. I think I'm going to skip over this one. This would usually be an example we just do in class. This is very similar to this one right here, and so it's this one I want to concentrate on because it's a little bit more complicated. So here I've got 5 outcomes, kind of, yeah, or excuse me, 5 different categories. So this is how long people survive after, I believe this is heart surgery, or if they're recovering from a heart attack and they own a pet. Interestingly, it is a statistical certainty, basically, that owning a pet increases your rate of survival, increases your survival rate after major devastating life events, including heart attacks, for instance. There's a lot of theories about why that is, but it does appear to be true. So I totally made up this data. This isn't a real study, but it does broadly mirror actual real studies. So what I've got here is the survival time, less than 2 years, 2 to 5 years, or 5 or more than 5 years after a heart attack, and whether the person owns a pet or doesn't own a pet. And so we're going to call A is they own a pet, B is they don't, C is they survive less than 2 years, D is 2 to 5, and E is more than 5 years. Right, so I've got 5 different events. The first event, or event A, is these outcomes. Event B is these. Event C is these. D is these, and E is these. Okay, that's really the way you want to think about that. So I'm going to talk through all of these, and I'm probably not going to write all of them down, but I'll talk through them all, and if you want to get numbers for all of them, you can. So probability of A and C. So A and C means they own a pet and they survived. Oh, it's not. Why won't it let me grab? There. Hey, I hit control, you turkeys. There we go. So it's they own a pet and they survive less than 2 years. So this is somebody who had a heart attack and then died within 2 years of their heart attack, and also owned a pet. So there were 25 of those people out of the 500 in the study. So the probability of A and C is 25 out of 500. Probability of C and D is the probability that they survived less than 2 years and survived 2 to 5 years. Well, that's not a thing that can happen. If you die before 2 years are up, you didn't live between 2 and 5 years. So the probability of this is 0. These two things are mutually exclusive, right? If we know that the person survived less than 2 years, then the probability that they survive 2 to 5 years is 0. Can't do both. One prevents the other. Probability of A or C is everything that's in A and also everything that's in C, right? It's this and also this stuff. So it's all of that stuff added together. That's the total number of outcomes out of 500 that we should look at. A way you can find that relatively quickly, like I can do this relatively fast and tell you that's 335 out of 500 by doing the following. Instead of adding up 135 and 25 and 72 and 103, although that does work, what I did was I looked at this plus this minus that, right? Because that's what the OR formula says, is probability of A plus the probability of C minus the probability of A and C. And that is 360 minus 25, which is 335, right? That's an easier, it's a quicker calculation. So that's the one I did. Probability of C or D is the probability that they survive less than 2 years or 2 to 5 years. which is exactly the same thing as 5 years or less, right? So one or, it can't be and, but it could be or, right? It would be this plus this, minus the overlap, which is 0, right? So I don't have to worry about the overlap. So this is 309 out of 500. Probability of A given C. So now we're going to start by given C. So we're only looking at this column, right? Because that's C. So within that column, what is the probability of A? Well, it's 25 out of 160. We're not out of 500 anymore because we're restricting our sample space to just C, which has 160 people in it. So it's 25 out of 160. C given A looks very similar, but now we're restricting ourselves to just pet owners. So within just the pet owners, what's the probability of C? 25 out of the 200 pet owners. So F is 25 out of 200. Probability of E complement. E was this one. So E complement is everything that's not in this, which is to say all this stuff, which we already found, right? That was 309 out of 500. We already figured that out. So E complement and C or D are the same thing, right? They're just written differently. Probability of E or E complement, that is the probability of being in here or being in here. Well, that's everything. So unsurprisingly, probability of E or E complement is 1. And in fact, that's always true. If you just think about what complement means, this says, what is the probability that you are either in E or not in E? And it's got to be one of them, right? There's no other options. You're either in E or not in E. So it's 100%. So just one is the probability here. Probability of E and E complement. What is the probability that you are both in E and also not in E? 0. You can't be in both, right? You're either in E or you're not in E, but you're not in both. So this, so I here is 0. 2 mutually exclusive events, anything that where one prevents the other one, right? A and B are mutually exclusive. If you own a pet, you can't not own a pet. C and D are mutually exclusive. If you survive less than 2 years, you can't have survived 2 to 5 years, etc. So if one prevents the other one, those are mutually exclusive. Are A and C independent or dependent? They are dependent. And so the way I can tell is if I look at the probability of A and the probability of A given C, they're not going to be the same. So the probability of A is 160 out of 500, which is 32%. Oh, sorry, that's C, I apologize. Probability of A is 200 out of 500 or 40%. The probability of A given C is 25 out of 160, which is much smaller. That's like, what is that? Like an eighth? No, it's not quite an eighth. It's like a sixth, something around there, 6th or 7th. So about, let's say 18%, something like that. So 25 out of 160 versus 200 out of 500 are not the same fraction. So A and C are dependent events because probability of A is not the same as the probability of A given C. So in other words, if someone survived less than 2 years, the probability that they owned a pet was very different than just the probability of owning a pet in general. I'm going to go ahead and skip L. No, I'm not going to skip L. I will show you how to do that because there is a thing that asks you to do that in the homework. So I'll go ahead and show you how to make a tree diagram. So we've got 2 different choices, right? They can either own a pet or not own a pet. And then within that, there's 3 choices of survival time, less than 2, 2 to 5, 5 or more than 5 years. So I'll go ahead and make a tree diagram of all that. Might as well get all of this done. I'm going to go ahead and erase this. So we've got 2 choices. We've got pet, no pet, pet, no pet. And then less than 2, 2 to 5, more than 5. Less than 2, 2 to 5, more than 5. Same thing over here. Okay, so let me put some probabilities on here because that's really what I want to show you here more than anything else. So if we look back at our chart here, there's a probability of 200 out of 500 that the person owns a pet and 300 out of 500 that they don't. Right, so I'm going to go ahead and put that on my whiteboard. So this is 200 out of 500. A little messy, sorry. This is 300 out of 500. Now, these are the interesting ones. So this right here, the probability that's going to go here in the less than 2 is the probability of surviving less than 2 years if you own a pet. Because notice, by looking for this probability right here, I'm implicitly saying that I'm on this branch, which is the pet branch, right? So given that I own a pet, or given that this person owns a pet, then what is the probability they survive less than 2 years? So so down here in the second layer is actually a conditional probability. Let's go back and look here. So within surviving 2 years, or within owning a pet, right? Because we're given that we own a pet, then what's the probability that we survive less than 2 years? What's 25 out of 200? And the other two are 72 and 103 out of 200. So what we've got here is, this is 25 out of 200, 72 out of 200. That says 2000. That's too many zeros. This guy is 103 out of 200. And so if I want to find the probability that someone survives less than 2 years and owned a pet, I would just multiply down the branch. I would do 200 over 500 times 25 out of 200. So let's do that real quick. So let me switch back to black. Probability of owns pet. So let's undo that. Probability of, no, I had that right. A and C is the probability of, wait, did I do this backwards? Do I write it as C and A? Yeah, whatever, I'll leave it. C given A times probability of A. Right, and so this is the same thing as C and A here. Right, that's kind of how I'd want to think of it. Is the probability of C given A times the probability of A. Well, the probability of C given A is this one. Probability of surviving less than 2 years, given that you own a pet, times the probability of owning a pet. Right, that's what this says. So this guy right here is 25 out of 200 times 200 out of 500, which is 25 out of 500. Which, what I'm doing there is I'm just canceling, right? Cancel your fractions, makes it easier. Or cancel when you're multiplying, it makes it a lot easier. 25 out of 500, which is, as we know, the probability that we found first, probability of A and C, or C and A, right? Either one's the same thing. And all the other ones are the same. These would be conditional probabilities as well. These are all going to be out of 300, right? Because we're restricting ourselves to just B here. So it's all out of 300 instead of out of 500. Okay. I think that is probably the last thing I want to say here. The place you end up using this, by the way, in the homework is near the very end on the cookie problem. This guy eating chocolate cookies and butter cookies, and you want to find the probability of getting each one. So don't forget that it's conditional probability for your second layer. Like, that's very important. Because by finding this probability here, we're assuming that we're down this branch, which is down the pet branch, right? So you have to take that into account. So you have to have conditional probability here. Okay, let me go back to the main notes here. Make sure that that's all I wanted to say. It is. That is all that I wanted to say about probability. That should give you the ability to do all of the questions on the homework, I believe. And if you're having any problems, of course, please come to the discussion sections, and I will see you then. I skipped. Don't worry about the fact that I skipped some of these. This event was really just an in-class practice thing. You are totally welcome to do it. You could 100% handle it without any help from me. Same thing, I would recommend that you do these guys to check out, to make sure that you can do the Venn diagrams and use all the formulas properly. And if you're looking for a summary of all the things that we did, I made a summary page at the end of the notes. I don't remember if there was a summary page at the end of the first or second notes, but there is from chapter 3 onward, where I just summarized the various formulas and a couple of main points. And so one thing I really want to point out is there's really only two formulas, right? There's this one and there's this one. And that's really it. Like, that's all the formulas that we have. And so there's not that much to remember here. So you're really looking at these two. And if you're trying to figure out, well, which one do I use? They asked for A and B. How do I know which one to do? Because they both have and in them. Well, you just look for the one that's got, just look for the information that you have in the problem and see which formula seems appropriate. That really is the way to do it. And then mutual exclusivity and independence. Mutually exclusive, two events are independent, are exclusive if one prevents the other one from happening. You can also think of them as sharing no outcomes, and you can also think of it as probability of and is 0. All those things mean the same thing. Two events are independent; they don't affect each other. So x and y are independent if probability of x given y equals probability of x, right? So y didn't affect x. Oh shoot, I felt like there was one more thing I wanted to say, but I'm not thinking of it right now. So I will just go ahead and leave it right there. And so I guess I'm gonna stop there and see you in the next video. So I hope this one wasn't too long. We'll see how long it was. All right, I'll see you then, or possibly in the discussion section.